Okay, so from the previous video, we actually discussed about the J, the electric, uh, the current density. The J is actually equals to the sigma E. So this sigma is actually the conductivity, and this one is the electric field. And we did proof for this formula. We proved that this formula is actually equivalent to the Ohm's law, which is V is actually equals to IR. Okay, so after discussing the subtopic from this subtopic from the previous video, so let's move on to some examples for to how should I say that? So let's move on to the example by showing the question of this formula J equal to the sigma E. Okay, so let's move on to the first question. Okay, examples. So for the first questions, let's say I have my potential difference. So my potential difference is actually 40 volts. Okay, so I have, of course, this one considered to be axis in wire X. So I have my wire X here. Okay, so and my resistance is actually 20 ohm and 20 ohm resistor, and we have the length for the wire X. So this is Lx. So I consider this Lx is 5.0 meters. Okay, so the cross-sectional area. So the cross-sectional area basically is 0.16 times 10 to the power of -6 meter square. Okay, so this is the information that given by the questions. So for the first question, what is the current that exists inside the wire? Okay, so what we need to do is actually find out what is the magnitude for the electric current that exists inside the wire X. So we have V, we have R. Basically, we can strictly use the formula from the Ohm's law, which is V is actually equals to IR. Okay, so this is 40 and I is the one that we need to find. Okay, then this one is 20. So basically I get for my electric current is actually 2 ampere. Okay, so this is how we find the electric current. And for the second question, the question is actually asking the conductivity for the wire. Okay, so what we need to do is think about what is the formula that is actually involving the conductivity. Okay, so from the basic, we actually know that resistivity is actually reciprocal to the conductivity. Okay, so from this one, I can see that I actually can apply the formula from the resistivity. So the resistivity, the formula that actually involves the resistivity is the formula of resistance. So the resistance is actually R is actually equals to the rho L over A. Okay, so the rho L over A, I can change it into the L over sigma A, and this is R. Okay, so the R, which given by the question, is actually 20, and what will be my L? So my L is actually 5. So this sigma, okay, so this is the cross-sectional area. So 0.16 times 10 to the power -6. Okay, so the sigma after calculating, So what I get is actually 1.563 times 10 to the power of 6. And if the SI unit for the resistivity is ohm meter, and basically the conductivity will be reciprocal, which is ohm -1 and m -1. So this is the concept. Alright, so this is how we find the conductivity, which is sigma. Okay, so let's move on to the question C. So the question C is actually asking for the current density. So the current density is actually J. Okay, so we have the sigma and we have the, so let's see what we have here. So we have the sigma. So the formula that involving the current density and the sigma is actually J is actually equals to the sigma multiplied by E. So the question is, the E is actually not given, and hence what we need to do is actually convert it into the another formula. So we know that E is actually equals to the potential difference divided by the length of the wire. Okay, so E, hence I can say that E is actually V over L. So this L is the length of the wire X, of course, and this is how we calculate the current density, and this is 1.563 times 10, so let me just scroll for a bit, times 10 to the power of 6, and potential difference. So the potential difference given here is actually 40, and this is 40 volt. And what will be our L? And my L is actually 5 meters. Okay, let me just observe for a while. Okay, so for the final answer after calculating, and what I get is actually 1.250 times 10 to the power of 7. Okay, so this is ampere per meter square. Alright, so this is the first question. For the first examples, for the formula J is actually equals to the sigma E. And I think, okay, so let me just check for a while. Yeah, this is actually the topics for the J is actually equals to the sigma E. Okay, so for the second examples, so let's move on to the second example. So let me find a space that is much bigger. Okay, I think this is the place. Okay, so for number 2, so for number 2, let's say the question the question provide us the resistivity of a certain wire. So the resistivity of the certain wire is actually 3.2 times 10 to the power of -8 ohm meters. Okay, so for the second information, which is the electron density, so the electron density given here is actually 2.0 times 10 to the power of 29 per meter cube. Okay, so for the third one, the electric field is actually 5.0 volt per meter. So this is the three information given by the question. Okay, so for the first question, the question is actually asking for the drift velocity. So what is the drift velocity? Okay, so what we need to do is actually find out what is the formula that is related. So for the first for my idea, what we have here is actually I is actually equals to NEVA. So I just try this formula. I do not sure whether it is correct. So let me just try for a while. So from I and A, I can convert it into NEV. So NEV and this I over A, basically what we get is current density. So current density is J and EV. Okay, so I just write here. So this J and this this J, the question did not provide us. So what we need to do is convert it into another formula. So another formula, what I think is actually the J has two formula, which is I over A, and for the another formula basically is sigma E, and this is NEV. Okay, I have E, but the question given is actually the resistivity. So but here what we have here is actually the conductivity. So the conductivity changed to the resistivity is actually the reciprocal. So the reciprocal NEV. Alright, so let me check uh, whether the formula which exists in this whether the variable that exists in this formula that we have the information. Okay, so we have E here, and we have the resistivity, and we have the electron density, and we have the electron is actually a constant, so we have the drift velocity. Okay, so we have all the information that we needed, and we can calculate it. So this is E, and the resistivity given is actually 3.2 times 10 to the power of negative 8, and this is 2 times 10 to the power of 29 for the electron density, and this is the electron 1.6 times 10 to the power negative 19, and this is V. Okay, so let me see whether the what is the answer. So 3.2 times 10 to the power negative 8. Okay, so alright, so the final answer that I got is actually 4.883 times 10 to the power of negative 3 meter per seconds. Okay, so this is how we find the drift velocity. Okay, so this is part A. And what about part B? And B is actually asking for the current density. So the current density, we can strictly use this formula. So J is actually equals to NEV, and the electron density is 2 times 10 to the power 29, and E is actually 1.6 times 10 to the power negative 19, and the drift velocity that we get from the previous question is 4.883 times 10 to the power negative 3. Okay, so the final answer that I get for the current density is actually 1.563 times 10 to the power of 8 ampere per meter squared. So this is how we find out the drift velocity and the current density from the question which the information provided by the questions. Okay, so what we need to do is actually understand the question and find out what is the formula that is actually applicable. Okay, so we have done for the examples. For the formula J is actually equals to sigma E. Okay, so let's move on to the final subtopic of this chapter. So the final subtopic of this chapter is actually the mean free time. Okay, so this is the mean free time. So I think I should clear all the, okay, never mind. So we just continue here. Okay, so mean free time. So what is actually the mean free time? So the mean free time is actually the average time, so this time basically is time t between two collisions between, okay, so between the collisions of the free electrons with the lattice atoms. So basically the mean free time is actually the average time between the collision of the free electrons with the lattice atoms. Okay, so let's say I have my lattice atoms, and this is the first and the third, second, third, and fourth, fifth, and sixth, seventh, eighth, ninth. Okay, so this is the lattice atom which exists inside the wire, and let's say the the free moving electron is actually moving this way. So the direction of the free electrons move from the left to the right. It means that the electric field is actually moving from the from the right to the left. Okay, so let's say my free electron is actually heading to this lattice atoms, and the electron is actually accelerated by the electric field, of course. So the accelerated electron is about uh, to collide with these lattice atoms. So between this interval and between this distance, okay, so let me just draw it clearly. And between this distance, so this distance, I assume this distance as d. I denote this distance as d. And between this distance, there's actually the time interval. The time interval which the free electron is about to collide with the lattice atoms. So this time interval is what we set as the mean mean time. Sorry. So this time interval is actually the mean free time. So why are we call it as mean free time? Mean, this is because we assume all the free electrons inside the wire are actually have the same time interval between the collision of the lattice atoms. Okay, so I repeat again. So the reason why we called it as the time interval as the mean free time is because we assume that all the free electrons which about to colliding with the lattice atoms have the same time interval. So this is what we call mean free time. Alright, so we have done for the introduction of the mean free time. So let's move on for some of the derivation of the formula. So okay, let me just Okay, so this one will do. Okay, so derivation. So let's look for some derivation of the sigma is actually equals to the n e squared t over n. Okay, so let's say I have a wire. So the wire is here and the direction of the electric field is this way from A to B, and of course we know that the electric current is actually also in the direction from the A to B, and this is I. Okay, so of course between point A and B we have the potential difference. So the potential difference is actually the V. Alright, so first and foremost, what we have here is actually the electric force. So the electric force exerted by the free electrons, by the free electrons, so the electric force exerted by the free electrons due to the electric field that accelerated the free electrons. So what we have here is actually F is actually equals to EE. So normally what we write here is actually EQ, but since our subject is actually the electrons, so hence what we write here, we write it as E, capital letter E and small letter e. Okay, so this is EE, and we know that for the basic formula for the force, so the basic formula for the force is actually MA. Okay, so MA is actually equals to the EE, and hence what I can get here is actually the acceleration of free electrons. So the acceleration of free electron, what I get is actually EE over M. So this M is actually the mass of the electrons, free moving electrons. Okay, so this is the equation 1. Alright, so as the free electron is accelerated by the electric field, and hence we have here is actually the drift velocity of the free electrons, free moving electrons. Okay, so the drift velocity of the free moving electrons. Okay, so what the formula that we need to apply here is actually the V is actually equals to U plus AT. So this is the drift velocity and this is the initial velocity and this is the acceleration and this is what we call the mean free time. So this is the mean free time, and this U, basically the U is actually equals to 0. Why? This is because U is actually the random velocity when the electric field, so the electric field is E, when the electric field is not how should I say that, the electric field is not supplied. So remember we talked about the random velocity. So the random velocity has no net velocity. since the random velocity is much higher when the electric field is not supplied, so the motion of the free electron is very fast, and hence the fast how should I describe this? The fast of the so give me a second. How should I say that? So the fast moving electrons has no net velocity. So the no net velocity causes the drift velocity for the free electrons is actually 0. So let me just write it for the second point. So since the net velocity is 0, hence the initial drift velocity, so the initial drift velocity of course is the bar u. So the initial drift velocity is 0. Okay, hence I can say that v is actually equals to 0 plus at, and this is at. Okay, so this a I can directly sub it as ee over m, and this is t, and this is bar v of course. Okay, so we have done for the drift velocity. So let's move on to the other parts. Okay, so as for the other parts, so this one should be my question equation 1. Sorry, this one is the equation 1. Okay, so let's move on to another equation, which is I is actually equals to NEVA. So since current is the one that exists inside the wire, and what I need to do is actually derive for the drift velocity. So V is actually equals to the I over NEA, and this is the second equation. So by equating the both equation, which is 1 is actually equals to 2, and EET over M is actually equals to 1 over NEA. Okay, so let me just observe for a while. Okay, so if I about to derive for the electric field, so this is NI, and this is the N E square A and T, and this is the electric field. So I get the final formula is actually the formula of the electric field, and this is the equation 3. Okay, so after discussing for the current, what we have here is actually the current density. So the current density, so since the formula given here, we have the okay, where is the main formula that we need to derive? Okay, so the main formula is actually consists of this sigma. So what we need to do is actually find out the formula of the sigma. So since we discussed until the current density, so the current density has two formula, which is the sigma, which is the sigma E and I over A. Sigma E and I over A. So what we choose for the current density, the formula of the current density is actually this one. This is the formula that we need. Okay, so this I have my equation 4. Okay, so So let's substitute the equation 3 into 4. So this is J is actually equal to the sigma, and this is mi, and this is ne square a t. Okay, so after deriving until here, so what we need to do is actually change this j into I over a. So since the final formula does not consist of j, which is the current density, so what we need to do is actually convert it into another form, and this this other side will remain it. Okay, so what we need to do for the next step is actually simplify it. So since I can be cancelled and the cross-sectional area of the wire can be cancelled as well, so the final formula in which the formula for the conductivity is actually the Ne square T over M. So this is the final formula. Alright, so this is actually the steps that we need to, okay, sorry. So this is actually all the steps that we need to do in order to derive this formula. So the step is actually quite longer. So what we need to do is actually think about the variables that is actually exist inside this wire. So the first variable, for the first variable, for the free moving electrons, we have the drift velocity, and the drift velocity is actually due to the acceleration of the free moving electrons. So the acceleration of the free moving electron is actually due to the electric field. So this is the free moving electrons. As for the electric current, in terms of electric currents, we have the current density. Okay, of course we have the current density. So in order to conduct electricity, we have the conductivity. So the conductivity is actually, of course, the reciprocal of resistivity. So this is actually the variables that is actually related to both electrons and electric current. Okay, so if we can think about these variables inside the and their own formula respectively, so we eventually can actually get the final formula, which is sigma is equal to Ne square T over M. So what we need to do is actually think step by steps and derive it until the formula emerge. Okay, so that's it for this for the derivation of sigma is actually equals to Ne square T over M. Okay, so let's move on to the final parts. So the final parts of this subtopics, which is the factor that affecting, okay, let me use another color, factors affecting the mean free time. So basically the mean free time is actually describing the time interval for the free electrons. Mean free time. Okay, so factor affecting the mean free time. So the mean free time is actually dependent on the conductivity and the resistivity. So So the mean free time of electrons is actually dependent on the conductivity and resistivity. So it is actually independent from the potential difference, independent from the electric field and others variables. So the factor that is actually affecting the mean free time is actually conductivity and resistivity. So how can they affect the mean free time? So let's move on to the first part. So for the first part, that is actually so for the first part that is actually affecting the mean free time is actually the temperature. Okay, so let's say I have my lattice atoms. So this is the lattice atoms, and this is the lattice atom of the wires, of course. So inside this lattice atoms, I have my free electrons. So this is the free electrons which inside the lattice atoms. So when the heat is actually supplied to the temperature, so we did learn from the chapter of the heat transfer. So we did say that the when heat is supplied and the lattice atoms of the material will begins to vibrate with larger amplitude. And this actually same concept. When the heat is supplied, the lattice vibration become increase and increase. So the lattice vibration increase in the lattice vibration. Okay, so let me just draw it. Okay, so increase in the lattice vibration. Okay, so for the first point, if the temperature increase, the vibration of lattice atoms increase. Of lattice atoms increase. So the increase of the lattice atoms. So what happened when the lattice atoms vibration of lattice atom increase? So when the lattice vibration increase, and it will eventually collide with the free moving electrons. So the collision and this will collide and this will collide, and all the lattice atom will eventually collide with the free moving electrons. Okay, so this thing goes to the other two sides. So when the colliding of the free electrons begins to increase, so I can say that the frequency of collision between the electrons. Okay, so between the electrons and the lattice atoms will increase. So what happens if the frequency of collision between the electrons and the lattice atom increase? So we actually have the formula, which is the frequency is actually equals to 1 over t. So this formula is actually not important. I just use this formula to describe the mean free time. Okay, so from this formula, if the frequency of collision increases, and hence I can see that the mean free time of the free electron is actually decreasing. So I can conclude that hence the mean free time decreases. This is the concept when the temperature of the metal increase, and the frequency of collision between the electron and the lattice atom will increase. Hence, the mean free time will decrease. Okay, so from the formula that we derived from the previous parts, this is the conductivity and this is the Ne squared T over M. And so from this formula, I can actually see that my sigma, which is the conductivity, is actually directly proportional to my mean free time. And this is the first one. And of course, if the reciprocal, so if I change this sigma to the resistivity, and hence what I get is actually inversely proportional to the resistivity. And from the previous parts, if the resistivity will if the mean free time will decrease, and hence I can conclude that the resistivity of my wire is actually increased. So I can conclude that therefore the resistivity will increase. Okay, so this is actually the factor that affecting the mean free time. So for the first one, when the temperature increase, the vibration of the lattice atoms increase. So the vibration of the lattice atom increase will causes the frequency of collision between the electrons and the lattice atoms increase. Hence, the mean free time of the mean free time collision of the free electrons and the lattice atom will decrease. So the decrease in the mean free time will causes the resistivity of the wire to increase. So this is actually the overall concept that we have. And as for the graph of the resistance against the temperature, okay, so this is ohm, and okay, so initially I have my the resistor of the wire. I denote this one as R0. So initially my wire, the resistance of my wire is actually R0 at the room temperature, I assume. So when the temperature of the wire is increased, so hence what I get for the graph, for the curve, is actually in this form, which is when the temperature keep increasing, the magnitude for the resistance will also increase. So this is the concept. Okay, so alright, so actually the mean free time consists of only one factors, okay, which is the temperatures. Alright, so we have done for the mean free time, and let's move on to the another part, which is the additional part, which describing the semiconductor. So we are going to discuss about how is the semiconductor conduct electricity. Okay, so let's say so from the semiconductor, we did learn the semiconductor from the chapter heat transfer. So let's say this is the semiconductor and this is the valence band. So I hope you still remember. So this is the valence band and this is the conduction band. So we did discuss from the chapter of the heat transfer about the valence band and the conduction bands. So between these two bands, this is the semiconductor, of course. So within these two bands, this is actually a gap. So this is actually a gap, and we talk about we did discuss about the electrons is actually in this side, which is the valence band. It means that the electron, if the temperature is not supplied, the electron is actually keep bonding to the lattice atoms. So what we need to do is actually supply the temperature. So when the temperature is supplied and the electron is actually gain energy, so this electron is actually gaining energy. So hence the electron will actually eventually jump from the valence band to the conduction bands. Okay, so when the temperature keep increasing, hence more electron is actually will move from the valence band to the conduction bands. So okay, so let me just write it in terms of sentence. So when the temperature increases, so the temperature increases, the electrons is are able to detach from the weak bonding from the weak bonding with the lattice atoms, okay, so hence I can conclude that the conductivity is increasing. Okay, is increasing. So this is the concept that is actually what I discussed just now. So when the temperature increases, the electrons are able to detach from the weak bonding with the lattice atoms and gain energy, and hence the conductivity is increasing. From this diagram, and when the temperature is supplied, the electron is actually gaining energy. So the gaining energy for the electrons will eventually jump from the valence band to the conduction bands. So this is actually the concept for the semiconductor. Okay, so as for the graph, so I have my resistor and I have my temperature. As for the graph, so the initial resistance for the semiconductor is actually quite high. Okay, so this is R0. So initially we have the high resistance of R0, and when the temperature is supplied, hence the resistance will eventually decrease. So this is the concept that we get. So when the temperature is increasing, and hence the resistance of the semiconductor will eventually decrease. This is because the electron density for the semiconductor is so I repeat again. This is because the free electron density in the conduction band is keep increasing, and hence the conductivity of the semiconductor will increase with temperature. Okay, so this is the concept. Okay, so let's move on to the final conductor, which is the superconductor. So the superconductor is actually the conductor which conduct electricity conducts electricity with sorry, okay, let me just erase this one, with zero resistance. So the superconductor is actually the conductor that conduct electricity with zero resistance. So if we are about to conduct the electricity to allow the conductor to conduct electricity with zero resistance, so the temperature for the surroundings um, so the temperature for the surrounding must be extremely low. Okay, so the sentence is actually not complete. At sufficiently low temperature with or I can say that it is the critical temperature. So if we wish to conduct the electricity with zero resistance, and we must allow the conductor exist at the condition of low temperature, or I can say that as critical temperature. Okay, so as for the example for the superconductor, so the example of the superconductor is actually mercury. So mercury, the critical temperature is actually 4.2 Kelvin. As for the another superconductor, which is lead, so the lead, the critical temperature is actually 7.2, which is higher than mercury. Okay, so let's see what is the graph for the superconductor. So let's say I take the mercury as the examples. So the mercury, the graph for the mercury, and this is the T, and this is O. Okay, so the graph, what we get here is actually this is 4.2, of course. So this is actually a straight line, and after the straight line, the temperature will actually increase uniformly. Okay, so when the temperature is critical, the resistance will actually eventually decrease strictly until zero. Okay, so this is the example for the graph of resistance against temperature for the mercury. Okay, so let's talk about some usage for the superconductor. So what is actually the usage? So the usage for the superconductor is actually the electric generator. So some of the certain electric generator requires zero resistance to work efficiently. Okay, so electric generator made by the superconductor with 99% efficient. So the 99% efficient we consider is actually almost have the zero resistance. So okay, so this is the first example. As for the second example, we have MRI scan. So MRI scan is actually the scanning for the whole body. So this MRI scan is actually made up from the electromagnetism. electromagnetism. So MRI scan actually consists of zero resistance when scanning the body of the human. Okay, so this is two of the examples of the superconductor that is used for our daily life. Alright, so we have done for the whole chapter of the electric current. So we have done for all the subtopic. So I hope you can understand. So I think we stop here now. So if there's any any question need to be asked, please comment below this video. So I'll see you in the next video. Thank you. Bye.